Thanks for watching my video. Today we are going to discuss the geometrical interpretation of derivative. Okay, this is the geometric interpretation. Now let y equal to f of x be an equation of a function f. Okay, there is a function f, and let's say that equation of this function will be y equal to f of x. Okay, now let p of a comma f of a and q a plus h comma f of a plus h. This is the coordinate of x and y at the point P, and this is the coordinate of x and y in the point Q. Okay, be the 2 points close to each other on the graph of y equal to f of x as shown in the figure. So here this is the figure. Here is the xy plane. Okay, this is x, this is y. So this is f of a, and this is f of a plus h, because it increased by h. Okay, so h is nothing but the distance between these two. Okay, the gap between these two, and this is the point A. We say this is a plus h. So if you join this a and this one, right, so f of a, then this one will be joined with these things, f of a plus h, right, because this to this it increased by h. So that's why the function also will be increased by h. Okay, and this the meeting point will be the point P. So a, f of a is nothing but the x-axis, and f of a will be the y-axis. Okay, y coordinate. And similarly with point Q, here we take this is the meeting point. Okay, and here we draw a curve. So this is Q, a plus h, and f of a plus h. Okay, and we draw a tangent line here. Okay, this is a tangent line, and making an angle theta with the x-axis. Okay, now we're going to say this. So then the slope of second line PQ. So this PQ is what this line or this curve, this, okay, that what we call the secant. Okay, secant line. So this line will be nothing but f of a plus h minus f of a upon h. H is the difference between these two. Okay, or the gap or the distance between a and a plus h. Okay, since the tangent at P, so P is what we call at point P, this is, okay, this we draw this straight line touching P at this point. Okay, so that what we call the tangent line. Okay, since the tangent at P is the limiting portion of the secant line PQ, here at this point, okay, this, if you draw a tangent line, so this point is what we call the limiting point or the position of this secant line. Okay, so the slope of a tangent at P is the limiting value of the slope of secant line as Q approaches to P. Now if you take the limit as Q approaches this P, then this is what we call the limiting value. Okay, now as Q approaches P, so if this Q approaches P, then this h will be becoming smaller, and then at this point it will be 0, right, meaning h will tend to 0. So therefore the slope of a tangent at P, so if you will do in a geometry, okay, that the slope of a tangent line, slope, equation of slope, all these things we are going to discuss it. Okay, anyway, we are doing this first. Okay, so the slope of tangent at P is nothing but, we say that as Q approaches P, then this h will tend to 0, then is the limit as h approaches 0. So this, okay, this two, between these two, this is what we call the slope of a secant line. Okay, the slope of a secant line, limiting value plus this slope of a secant line. Here we do the limiting value of a slope of a secant line. The slope of a tangent at P is the limiting value of the slope of a secant line as Q approaches to P. As Q approaches P, h tends to 0. So therefore the slope of this tangent at P will be the limiting value as h approaches 0 times the secant line. Okay, this the slope of a secant line, this one, f of a plus h minus f of a upon h. So which therefore this is what we call the derivative. Okay, so f prime of a, derivative of a, which is equal to limit h tends to 0 f of a plus h minus f of a upon h. So we know that slope of a tangent at this point P, at point P, is what we call this tangent of this theta. Okay, the angle between this line and this x axis. Okay, so then is what we call tan theta. Therefore, well, theta is the inclination of tangent to the curve at point P and f of a with x axis, right? At this point, this is the curve, this one, this is the inclination. Okay, thus the derivative of a function f at a point a, point this is a point a, okay, represent the slope of tangent to f of x at a and f of a. So from this geometrical interpretation of derivative, we see that the derivative, okay, is nothing but the slope of a tangent. Okay, the slope of a tangent at point P, where P is the coordinate of P is n f of a. Okay, that will be the shortest proof for this geometrical interpretation of derivative. Okay.